Okay, so these are the D.5 Further Cosmology questions. Let's begin at the beginning, talking about the anistrophes in the cosmic microwave background. So, 1A, state the nature of those anistrophes in that radiation. And the mark scheme, I think, again, with a lot of these questions, the mark scheme addresses it well. It says temperature, or the peak wavelength, or the intensity of the cosmic microwave background radiation varies slightly, or slash is not constant in different directions. So there are some variations. I think that's what it means by the anistrophes. There are some differences in the wavelength and thus the temperature. And then 1B gets at why could that be? And the first two answers, quantum fluctuations. They say quantum fluctuation may have actually started the universe to begin with. That there was, matter energy exchange, like electron, positron, and matter antimatter collisions, creating gamma ray photon pairs, and then the gamma ray photons turning back into matter, and back and forth and back and forth and back and forth. When one of those things was actually a quantum fluctuation that resulted in more matter than antimatter, and that matter became the universe as we know it. Density perturbations, like kind of just perturbing the mass that's there, so that you have some areas of greater mass density, and then there's areas of less mass density. That's almost could be considered just chaotic motion. That that's just gonna happen in terms of that clumping. But the last one I didn't see in the notes, and it does kind of make sense. This is dipole distortion due to the motion of the Earth. Kind of like when you're making observations of the cosmic microwave background, you have to consider that your observations may be, it's very sensitive measurements, and those measurements may be distorted based on the actual motion of the Earth through space. So that's a fair point too. All right, and then our next question that is definitely D5 is going to be 2C, talking about the critical density of the universe. And specifically talking about, it says the density of a flat universe. This is that has like zero curvature. And so it says density of a flat universe. Okay, density for which the universe has zero curvature. I'm not even really sure what that means. But then it says density resulting in universe expansion rate tending to zero. I believe that was what I saw in the notes, or at least that's what made the most sense to me. I don't really. What the heck is that? Zero curvature. But is a density of a flat universe is a fine definition. But I feel like the follow-up question is, okay, cool. What's a flat universe? you know, it's like, oh yeah, the critical density is the density of a flat universe. Well, what's a flat universe? A flat Euclidean universe is a universe resulting in a universe whose expansion rate tends to zero. So there you go. All right, going back to 2C for a minute, we have, says, the density of the universe is about 32% the critical density. Keeping that in mind, we look at 2D. It says calculate the density of our universe. So it's 32% the critical density. Critical density is 3 times the Hubble constant over 8 pi g. It says the Hubble constant was 70, but that's 70 kilometers per second per megaparsec. So we have to convert. Here is the conversion. So convert the meters to parsecs, parsecs to light years, and then all of the distances cancel, and we're left with 1/seconds. Breaking it down to base units. We have to break it down to base units because of G. G's in base units. So I put 3 times that H number, 2.26981 times 10 to the negative 18 1/seconds. Put in big G, run the calcs, 9.22008 times 10 to the negative 27 kilograms per cubic meter. Then it's 32% of that, 0.32 times that. And we wind up with 3 times 3.0 times 10 to the negative 27 kilograms per cubic meter, which agrees with the Mark scheme. All right. And then 2e says, less than 20% of the matter is actually, of the universe is observable. How do galactic rotation curves explain this? All right, so 2e says 20% of the matter in the universe is observable. How do they know that? Based on galactic rotation curves. And the galactic rotation curves sounds super fancy, but when we talked in D5 about the speed of stars in a galaxy relative to the star's position from the center of the galaxy in the beginning of, closer to the center, the speed increases a lot as you move away. And that's because of, let's see, is that equation? I'm taking a look at the equations. Yeah, V equals radical 4 pi G density over 3 times R. That's the velocity of a star near the center of a galaxy based on the density of the galaxy that it's rotating around. But then as you get towards the outside, the outskirts of the galaxy, you can treat the galaxy itself as a point mass. You go back to like standard physics, and then the velocity starts decreasing gradually with increasing radius. That's the prediction from theory based on the observable matter. Then that's the graph there on the left. Then what they actually observed is that, yes, in the beginning, towards the center of the galaxy, stars do go faster, and then the rate by which they go faster as you move away does taper off, but then it doesn't start to decrease. It continues to increase, which does not agree with the matter that's observed. And so astrophysicists said, well, some mass there has to be accelerating these stars gravitationally, even though we can't see it. If we make these, these dark halo objects or whatever they call them to account for that missing mass, we can say that that dark matter exists in orbit around the galaxy. They don't really know what the dark matter is, but they know it's there based on the behavior of the stars. So in the Mark scheme for the 2 marks, it doesn't actually say to draw rotation curves, but it says 1, rotation speed of galaxies is larger than expected away from the center. That's what the graph on the left says. And in order to account for that, there must be more mass at those edges than is visibly observable, indicating the presence of dark matter. And I expected a follow-up saying, what do astrophysicists think this dark matter may be comprised of? But they did not ask that follow-up. So that was 2E. Let's see, what's next? 3B is next. So cosmological origin of redshift, I believe that's D4. And so we have here 3B wants to know, this is the cosmic scale factor versus time for the different versions of the universe. Is it an open universe, closed universe, or flat universe? So it says, draw on the axis a graph to show variation with time of the cosmic scale factor R for the flat model of the universe that includes dark energy. And that's 1 line and 1 mark. And so it shows the line, instead of tapering off where the cosmic scale factor eventually tends towards 0, instead the dark energy is going to continue that at a steady rate, the cosmic scale factor increasing. So that's the graph. That dark energy is providing the energy for that increase. So there's 3B. Okay, so next up is 4A through 4C. Homogeneous model of the universe says that it can be considered as a spherical cloud of matter of radius r and uniform density rho. Consider a particle of mass m at the edge of that universe moving with velocity v and obeying Hubble's law. Justify total energy of this particle is equal to the kinetic energy 1/2 mv squared minus 4/3 pi grr squared m. So that looks like it is a flat model where the total energy is 0. Yes, Mark Scheme would agree with me. In fact, they pretty much also do the math. Kinetic energy is 1/2 mv squared. Gravitation, the potential energy is gmm over r. And of course, there's a negative in there because the potential energy is negative. We take that to be negative, so that the sum of the kinetic and the potential is 0. And if we say that density is mass over volume, and then the volume of a sphere is 4/3 pi r cubed, we get that the mass is volume times the density. That's where the 4/3 pi r cubed rho, that's where that comes from. And so we slip in 4/3 pi r cubed rho into big M. So we take this guy, and then we stick that in for M. And so we wind up with E is 1/2 mv squared minus 4/3 pi g r squared m. I don't know why they said r squared. Why don't they just say r cubed? Especially since it's r cubed down here. So that's weird, but r times r squared is r cubed, so great. Yeah, it does say that for the second marking point, the second mark given, you do have to show the density is mass over volume, and volume is 4/3 pi r cubed. That substitution needs to be there. Apologies for not actually writing this stuff out in the boxes. Yeah, I'm just too lazy for that. I did write it out. I wrote it down here in my notes. But yeah. You, of course, should be doing all the writing in the box, full sentences, as clear as possible. Keep it in the box, not outside the box. All right, 4B. Critical density, there's 0 total energy. Show that critical density is, here's where it's 0, where it's critical density. And so that it's R critical is that what they're doing? Hold on a second here. Oh, I know what they did. All right, hold on. Let's go back to number 4A. I missed the part where it's GMM over R. So that over R, the R in the denominator actually cancels one of the radii, makes that R squared. This R, that should be rho, density. So I don't know why they just didn't use rho when they can clearly use rho down here. And so here, again, they're using, I don't know what they're doing here. This should be rho critical is equal to 3 Hubble constant squared over 8 pi g. Didn't we already do that? Oh no, we did that earlier. We actually used that formula to actually solve for some real values. But it says show that that's the critical density. So we're just using what they gave us over here and setting that equal to 0. So we have E is 1/2 mv squared minus 4/3 pi g rho r squared m. Okay. So yeah, using the expression that they actually gave us in 4A, we get that energy is 1/2 mv squared minus 4/3 pi g rho r squared m. And so when you set E to 0, the masses cancel, so I canceled them out, and I get 1/2 v squared is 4/3 pi g rho r squared. Now we got to bring in the Hubble constant, and we know that speed is Hubble constant times d, or times radius in this case, distance from center. So I slip in h naught r for V. So I get rho is 3/8 pi g, that's all the constants, v squared over r squared, but v is h naught r, so I put in h naught r for v. I get rho is 3/8 pi g, h naught squared over r squared, and so the r squareds cancel. So finally, I get rho is 3 h naught squared over 8 pi g, which agrees with the show that up at the top. Fun times. Notice it also says answer is given, so check working carefully to make sure that it matches. Please show you're working clearly. And then after all that work, 4C allows you to actually use that formula to find out what is the critical density, assuming that the Hubble constant is 2.3 times 10 to the negative 18 seconds to the negative 1. How kind of them, they actually gave it in base units instead of those stupid megaparsecs. All right, we use the expression from 4b, put in the numbers they give us, including big G, and we get 9.5 times 10 to the negative 27 kilograms per cubic meter, which agrees with the mark scheme, so good for us. All right, let's continue. Let's look at 5a and 5b. Outline. What is meant by dark energy? So what does the mark scheme have to say? It says dark energy fills all space, so I guess it's everywhere, okay, resulting in a repulsive force opposing gravity. That would maybe explain why speed increases as r from the center of the galaxy increases, the speed is increasing, so it's kind of like working against gravity. Also, opposing gravity means that's going to, it's not going to be the big crunch death of the universe. Gravity's not going to pull everything in together. That's what we saw, this resulting in a repulsive force opposing gravity. That's this curve right here. So that as time goes on, the cosmic scale factor will get bigger and bigger and bigger because of dark energy opposing gravitational attraction. Accounts for the accelerating universe, why the universe's expansion is accelerating, and it makes up about 70% of the energy of the universe. I wonder if they need that as the second point. It seems like kind of like an annoying fact to memorize. I don't know. I would say in terms of, this seems just like a throwaway answer. It's like, it's everywhere. Okay. But I would say that these 2 points are the most important for dark energy. And then 5b, the two candidates for dark matter. I knew this was a question somewhere. I thought this was going to be the follow-up for, where is it? 2e. I thought there was going to be 2f, where it's like, okay, so like what's actually causing this? What is this dark matter business? So what could dark matter be? Let's see what the mark scheme has to say. It could be a black hole. Could be a brown dwarf. I don't know. That's news to me. I've heard machos, the massive compact halo object, which is that invisible mass that accelerates stars near the edges of galaxies, causing for their speed to keep on increasing, could simply be a lot of neutrinos. I mean, neutrinos, they're very hard to detect. They're neutral. They don't react electrostatically. And they do have mass, so they would have gravitational influence. Or weakly interacting massive particles. Just things that have mass and don't really interact much, or WIMPs. This seems like a made-up particle. My personal, if I had to pick a favorite as to what I think dark matter is, I think it's machos. Massive compact halo object. What are those objects? I don't really know. They asked for two marks. So if I had to pick a runner-up, I would say neutrinos or WIMPs, because that WIMPs were in the notes. Brown dwarfs are weird. I thought brown dwarfs were actual real matter. Just like a brown dwarf is like a slightly bigger version of a gas planet. I don't know. That seems like news to me. Same thing for a black hole. Black hole is actual mass, but it has 0 volume. Whatever, let's move on. All right, so that was 5B. All right, let's take a look at 7A through 7C. So we have this, it says the amounts of mass, and it says this, a galaxy can be bundled in a sphere of radius r0. The distance of a star from the center of the galaxy is given as r. And this graph is kind of related to the galactic rotation curve, saying that as speed increases as the radius increases. And so for the first portion, this portion right here, the speed is going to be, that's the radical 4 pi g rho over 3 times r. For that portion. And then for this portion where the mass is constant, it's saying that is our graph. That is our equation, and it says show that, why that's true. All right. That wasn't hard. We know that centripetal force is force due to gravity, so mv squared over r is equal to gmm over r squared. Little masses cancel, one of the r's cancels, take the square root, and you get v is radical gm over r. Here's 7b. This is the galactic rotation curve. Galactic rotation curve, showing the velocity of stars as you move away from the center of the galaxy. Up to the point of r0, the velocity increases, but then even though theory predicts that the velocity should start to decrease as radius increases, when it says the observed variation of r shows that the velocity does increase slightly as you go. And so, yeah, there's 2 parts to that, so 2 marks. And then 7c says, explain using the equation NA, and in A, here, v equals radical gm over r. So I don't have to go back there. Let's actually write that down. V is radical gm over r, the equation from A. And the graph, why the presence of visible matter alone cannot account for the velocity of stars when r is greater than r0. Well, the velocity should be proportional to the square root of the radius. Oops, my bad. V is proportional to the square root of 1 over the radius. And so as the radius increases, the speed should decrease, not be constant or even increase slightly. So using the equation from 7a, v is radical gm over r, based on what theory predicts, that is not what is actually happening. So the visible matter alone, which is this is the visible. If it was visible matter alone, we would expect that relationship, and that's not what happens. So there has to be additional matter causing that to happen. Okay, we are approaching the end of this set. The next question is 8b. And it says, outline why a hypothesis of dark energy has been developed. And so let's take a look at what the mark scheme has to say. Type 1 supernova shows universe expanding at an accelerated rate. So the accelerated rate is important. So there's some energy pushing it apart, but also you should mention the type 1 supernova because those are standard candles. And we can use the type 1 supernova to get a good sense of luminosity versus apparent brightness to use as a sense of how far away the supernova actually is. And then it says the gravity of all the combined mass was expected to slow down the expansion of the universe and maybe even crunch it together. But observation, the accelerated motion of supernovas counters the hypotheses at the time. And so that dark energy is actually opposing gravity, and therefore dark energy is causing that acceleration. Otherwise, what the heck is causing the acceleration of the universe when theory predicts that gravity should either stop the expansion or bring everything back? All right, then we have 10A through 10C. They should be down here. Here we go. We have the cosmic scale factor versus time. And it said flat model when dark energy is ignored. What's the variation with time when dark energy is present? This one shows that the scale factor increases. I just know that it's the scale factor, like up to the present time is normal, but instead of kind of tapering off, if you include dark energy, the scale factor starts to increase. Like not even as a straight line, but as an increasing line. So I guess I should say that the slope is increasing. Slope is increasing, not decreasing. The line that's currently there has a either constant slope or a decreasing slope. And the dark energy is what's doing the pushing apart, the acceleration. And again, slope is increasing, not decreasing, when dark energy is present. All right, and then we have 10B. So they give us the density is 0.32 critical density, where critical density is 10 to the negative 26 kilograms per cubic meter. It says density of the observable matter in universe is only 0.05, the critical density. How is the remaining 0.27 of the critical density accounted for? Well, if observable matter is only 0.05, and we have another 0.27. Again, where is it getting the 0.27 from? That would be the 0.32 as our critical density minus the 0.05 that we're getting from the observable matter. So it's saying where is the other 0.27? And that can be accounted for with, of course, dark matter, a density of mass, of gravitational influence that is not readily observed. And you would need to explain that. So it's like dark matter says, unexplained mention of dark matter is not sufficient for the mark. I just explained it in the video. You need me to actually write it out? Oh, sheesh. All right, hold on. Yeah, so it provides a gravitational influence without any kind of electromagnetic radiation. It doesn't emit any light, hence being dark. I feel like just saying dark matter should be enough, but no. All right. So dark energy, density of dark energy is rho lambda delta c squared. I think they're getting that from E equals mc squared. Where rho delta is critical density minus rho m. What the heck is rho m? Oh, it gave that to us up here, right? Yeah, okay. The matter density of the universe is 0.32 times the critical density. All right, so let's write that down. Rho m is 0.32, the critical density. And then it says how much dark energy is in 1 cubic meter of space. All right, 10C, interesting question. So we have the density of dark matter is rho delta c squared, where rho delta is rho c minus rho m. Calculate the dark energy in a cubic meter of space. So rho m is 0.32 critical density. That was given in 10B. Yeah. And then it says that the density of the dark matter is rho delta c squared, where rho delta is rho critical minus rho mass c squared. Rho m, or the mass for our universe, rho m is 0.32 rho critical. So rho critical minus 0.32 is 0.68 rho critical. So 0.68 rho critical c squared equals 0.68 times 10 to the negative 26 kilograms per cubic meter. That was given up here. Rho critical is 10 to the negative 26 kilograms per cubic meter. Then, but that says per cubic meter, and actually wants to know how much energy is that. So then we multiply times a cubic meter to get rid of the meter squared. That's why they asked about a cubic meter of space. So we get 6.8 times 10 to the negative 25 kilograms C squared. Now that doesn't match up with the mark scheme, but remember that C is an actual number, but I'm out of space, so I'm going to zoom in a little bit here and say DE. I'm going to change colors, make it blue. DE, the dark energy, 6.8 E negative 25, and that's C squared, so that's 3E8, 3E8. And we wind up with kilograms meters squared per second squared, or joules. We're talking about energy here, right? And so that winds up being, oops, I done goofed. I put 0.68 times 10 to the negative 26 is 6.8 times 10 to the negative 27. That was my bad. So this down here is not 6.8 times 10 to the negative 25, it's 6.8 times 10 to the negative 27. 27. And that finally gets us to 6.1 times 10 to the negative 10 joules, and that does agree with the mark scheme. I kind of like that question. And we have two more. We have 13A and 13B. So let's see. Look at this funky curve. Rotation curve of a nearby galaxy. Interesting. 13A and 13B. So here's 13A based on this graph, and 13B. So graph shows the velocities. It's a rotation curve. We have radius in kiloparsecs. Oh, fun. And then velocity is in kilometers per second. What is the rotation velocity of the stars? 4 kiloparsecs from the center. The average density is 5 times 10 to the negative 21 kilograms per cubic meter. It says that the core of the galaxy has a radius of 4 kiloparsecs. And so the speed near the core of a galaxy is radical 4 pi g over 3 times r. We have the density in kilograms per cubic meter. Great. It's going to get the velocity in meters per second. Fine. But the radius is in kiloparsecs. I'm going to need it to be in meters. All right, there is my radius, my separation in meters. And that's a lot of numbers, but when you work the numbers through, you get about 146 kilometers per second, which is what the mark scheme says, so yay. All right, that was 13A, and then 13B is the last guy. It says, why rotation curves are evidence for the existence of dark matter. We've talked about this before. Mark scheme says rotation curves were expected to decrease outside of the core, but in fact they do not. A flat curve suggests evidence of matter of mass that cannot be seen, and we call that dark matter. Alrighty, and that is it. And that's it for the solution videos for option D. Thanks.